After the universe cooled from the Big Bang, precise measurements show it contained almost nothing but hydrogen and helium. Under those conditions, gravity does not wait. Gas gathers density, rises, and collapse follows. Without heavier elements to release heat efficiently, those collapsing regions could not fragment into small stars. They had to form enormous ones. Instead, objects tens to hundreds of times the mass of the Sun, burning hot, bright, and brief. Yet when modern telescopes scan the early sky, even with infrared eyes tuned for the cosmic dawn, none of these giants appear. Their absence carries information as real as any detection. That trail begins with Part 1. If these metal-free giants had to exist, why has no one ever seen one? If the early universe followed the same physical laws we test in laboratories today, then its first stars were not optional features, they were forced outcomes. Measurements of the cosmic microwave background and Big Bang nucleosynthesis show that after the first few minutes, the universe contained almost nothing beyond hydrogen and helium. No carbon, no oxygen, no silicon. In that environment, gas could not remain diffuse indefinitely. Gravity increases density wherever matter collects, and as density rises, collapse proceeds, unless an opposing mechanism removes energy fast enough to halt it. In a medium without heavier elements, that opposing mechanism is weak. The result is unavoidable compression into the first luminous objects. These objects are known as population 3 stars. The term does not describe age alone, it specifies composition. Population 3 stars form from gas, made almost entirely of hydrogen and helium, with metallicity effectively equal to 0. In astrophysics, metals include every element heavier than helium because those elements provide efficient pathways for cooling. Carbon and oxygen radiate energy through fine structure lines. Dust grains allow gas to shed heat and fragment. Remove those channels, and gas clouds behave differently. They stay hotter, they fragment less. The characteristic mass scale rises. Numerical simulations that include gravity, hydrodynamics, and radiative transfer repeatedly converge on the same outcome. The first stars should have been massive, often tens to hundreds of times the mass of the Sun, with surface temperatures exceeding 10 to the 5th Kelvin. A star of that size burns fuel rapidly. Hydrogen fusion proceeds faster at higher core temperatures, and radiation pressure grows strong. Luminosity scales steeply with mass. For comparison, a star with 100 solar masses can emit close to 1,000,000 times the luminosity of the Sun, with most of that energy emerging in ultraviolet wavelengths. These are not subtle objects. If they formed in large numbers and lived long enough, their combined output would have reshaped their surroundings, ionizing neutral hydrogen and altering the appearance of the early universe. This expectation is not speculative language. It follows directly from the equations of stellar structure, tested against observations of massive stars in nearby galaxies, and from simulations constrained by observed cosmic parameters measured by Kobe map and Planck. When those same equations are applied to primordial gas, they leave little room for alternatives. Yet when astronomers look toward the cosmic dawn, the sky does not show individual stars matching these properties. The absence is persistent, even as observational tools improve. Modern searches focus on infrared wavelengths because cosmic expansion stretches ultraviolet and visible light emitted billions of years ago into longer wavelengths by the time it reaches us. The James Webb Space Telescope was designed around this requirement. Its mirrors, detectors, and instruments were optimized to capture faint infrared signals from the first few 100 million years after the Big Bang. JWST's NIRCam and NIRSpec can probe redshifts beyond 10, where population 3 stars are expected to have formed. The mission goal includes tracing first light and the onset of reionization. Despite this capability, JWST does not return images of isolated metal-free giants. Instead, it reveals compact galaxies, clusters of stars, and emission lines that hint at hard radiation fields without resolving the sources into individual primordial stars. This is not an observational failure. It is a constraint. In astronomy, what remains unseen under well-defined conditions narrows the range of what could have happened. Non-detections, when instruments are sensitive enough, eliminate entire classes of models. One reason for the absence lies in scale and timing. Population 3 stars are predicted to form in small dark matter halos, often with total masses of only a few million solar masses. These halos host only a handful of stars at a time. Even if a single star shines intensely, its total contribution can be diluted by distance and cosmic expansion. At redshifts above 15, light travels more than 13 billion years before reaching us, losing energy along the way. A blaze at the source becomes a faint infrared whisper by the time it enters a detector. Another reason follows from stellar lifetimes. Massive stars exhaust their nuclear fuel quickly. A star 100 times the mass of the Sun may live only 2 or 3 million years. On cosmic timescales, this is brief. The window during which such a star exists, shines, and remains unobscured by surrounding material is narrow. Observing one directly would require catching a rare event in a small volume at precisely the right epoch. Probability alone reduces the odds. Gas dynamics further complicate matters. The first stars form within dense infalling clouds. Radiation from the star ionizes nearby hydrogen, creating an H2 region that can be shrouded by residual gas and dust-free yet optically thick material. While metals are absent, electron scattering and neutral hydrogen absorption still alter the emerging spectrum. What leaves the star may not travel unimpeded into intergalactic space. By the time it escapes, its signature may resemble that of a compact stellar population rather than a single object. The practical outcome is that astronomers often search for indirect evidence. Hard ultraviolet radiation produces specific emission lines in surrounding gas, such as singly ionized helium. A strong heat a second, 1,640 angstrom line when redshifted into the infrared, suggests an ionizing source hotter than typical population 2 stars. JWST has detected such features in a few distant systems. Each detection prompts careful analysis, because low metallicity star clusters can mimic similar signatures. Distinguishing between a truly metal-free population and a merely metal-poor one requires precise abundance measurements and modeling. If population 3 stars existed, they must have altered their environment. If they altered their environment, traces of that alteration should persist in gas chemistry ionization states and later generations of stars. Astronomers therefore treat the early universe as a layered record. Instead of looking only for the original actors, they examine the consequences of their actions. This approach echoes a long tradition in science. Edwin Hubble, whose observations established the expansion of the universe, framed exploration as an empirical process, rather than a search for spectacle. Equipped with his 5 senses, man explores the universe and calls the adventure science. The statement emphasizes method over outcome. Data guide interpretation, even when the objects of interest remain beyond direct view. Within this framework, not seeing becomes informative. JWST's sensitivity sets upper limits on how many massive luminous stars could exist at a given epoch without being detected. Those limits feed back into models of star formation efficiency, initial mass functions, and feedback processes. If too many population 3 stars formed, reionization would proceed faster than observed. If too few formed, the enrichment of later stars would be inconsistent with measured abundances. The viable range narrows. The current picture suggests a universe that formed its first stars, quickly allowed them to act briefly, and then moved on. Metals produced in their interiors or released at their deaths altered cooling pathways, enabling smaller stars to form. Subsequent generations, population 2 and population 1, dominate the observable record. The originals recede into inference. Their role is preserved not as points of light, but as constraints embedded in data. This tension between necessity and absence is the core of the puzzle. Physical laws require that metal-free stars formed under primordial conditions. Observations show a universe already enriched and structured by the time our instruments can resolve individual sources. The gap between those facts drives ongoing research. It motivates deeper surveys, refined simulations, and careful interpretation of every spectral line. The search continues, with discipline rather than certainty. Each new dataset tests whether the early universe left room for these giants to appear and vanish without leaving a direct trace. The answer does not rest on a single image, but on consistency across independent measurements. And as those measurements accumulate, the focus tightens, carrying us forward to the next examination. Part 2. How can a star be metal-free when everything today is full of atoms beyond hydrogen? If carbon, oxygen, silicon, and iron are now found in planets, oceans, air, and living cells, then a hard physical problem appears immediately. None of those atoms were present at the beginning. Observations of the early universe show that everything familiar today had to emerge from a starting point that contained almost nothing beyond hydrogen and helium. This is not an assumption built from theory alone. It is a result anchored in measurement. When astronomers measure the cosmic microwave background and compare it with nuclear reaction rates tested in laboratories, they find a narrow and consistent outcome. In the first few minutes after the Big Bang, conditions allowed only the formation of the lightest nuclei. Hydrogen formed first. Helium followed. A trace amount of lithium appeared. Reactions stopped there, not because heavier atoms were forbidden in principle, but because the universe expanded and cooled too quickly for further nuclear assembly. The densities dropped. Temperatures fell below the thresholds required to bind larger nuclei. From that moment forward, the universe entered a long chemical pause. This pause is not a gap in knowledge. It is a boundary enforced by physics. Heavier atoms require sustained high temperatures and pressures over long periods. Those conditions do not exist in free space. They exist inside stars. Stellar interiors compress matter to densities millions of times greater than those of interstellar gas. Temperatures rise to tens or hundreds of millions of Kelvin. Under those conditions, nuclei collide often enough to overcome their electrical repulsion and fuse into heavier elements. Without stars, the periodic table would end almost as soon as it began. The idea that stars are factories of atoms is now supported by decades of observation. Spectroscopy shows clear fingerprints of elements in stellar atmospheres and in the gas expelled by dying stars. Meteorites preserve isotopic ratios that match nuclear reactions predicted for stellar cores. Supernova remnants reveal expanding shells rich in oxygen, silicon, calcium, and iron. These are not abstract conclusions. They are measurements repeated across different environments, instruments, and research groups. Yet this creates a deeper puzzle. If stars are required to make heavy elements, then the very first stars must have formed without them. There is no circular escape. The first generation could not inherit carbon or oxygen from earlier stars because none existed. Their composition had to reflect the primordial gas left by the Big Bang. That is what astronomers mean when they describe population 3 stars as metal-free. The term does not deny the existence of atoms. It specifies which atoms are present. Hydrogen and helium dominate. Everything heavier is absent, to a degree that matters physically. The absence of metals changes how gas behaves. In modern star-forming regions, cooling is efficient. Carbon monoxide radiates energy. Oxygen lines carry heat away. Dust grains provide surfaces that help gas shed thermal energy. Cooling allows clouds to fragment into many small pieces, producing stars similar in mass to the Sun or smaller. Remove metals, and this entire pathway disappears. Gas remains warmer. Pressure resists fragmentation. Collapse proceeds on larger scales. The outcome is fewer stars, but each with far greater mass. This is not a stylistic description. It is a quantitative one. Simulations that include only hydrogen and helium cooling predict characteristic stellar masses tens to hundreds of times larger than those formed today. When even a small amount of metal enrichment is introduced, the mass scale drops sharply. Metallicity acts as a control knob. Turning it slightly changes the entire structure of star formation. That sensitivity makes metallicity a powerful forensic tool. Astronomers measure metallicity through spectral lines. Each element absorbs and emits light at specific wavelengths. When those lines are weak or absent, limits can be placed on elemental abundance. In nearby galaxies, metallicity maps reveal gradients shaped by star formation history. In distant systems, metallicity constrains how much prior stellar processing has occurred. A truly metal-free object would display a spectrum dominated by hydrogen and helium, with no detectable contribution from heavier atoms, even at high sensitivity. This is where population 3 stars becomes central to cosmic history. They represent the bridge between a simple universe and a chemically complex one. Once they form, they immediately begin altering their surroundings. Their intense radiation ionizes nearby hydrogen. Their short lifetimes end in violent deaths or collapses that release newly formed elements into space or lock them into compact remnants. Either outcome changes the chemical state of the environment. After the first stars act, the universe is no longer pristine. Evidence for this transition does not come from nostalgia about a lost epoch. It comes from the chemical record preserved in later generations of stars. In the halo of the Milky Way, astronomers have identified stars with extremely low metallicity. These objects formed early, before the interstellar medium was heavily enriched. Their atmospheres preserve the composition of the gas from which they formed. Some show abundance patterns that can be explained only if a single massive supernova contributed most of the metals. This points back to an era dominated by rare, powerful stars rather than many small ones. The technique resembles archaeology. Instead of digging into soil, astronomers dissect spectra. Instead of artifacts, they analyze elemental ratios. Iron relative to carbon, magnesium relative to calcium. Each ratio narrows the range of possible progenitors. In some cases, the data match models of massive metal-free stars undergoing core collapse or pair instability explosions. The stars themselves are gone. Their influence remains encoded in chemistry. This chemical reasoning aligns with observations of the distant universe. Galaxies seen at high redshift often display low metallicity compared to nearby systems. Their light suggests rapid star formation, followed by incomplete enrichment. When combined with reionization constraints from cosmic microwave background polarization and quasar absorption spectra, a consistent timeline emerges. The first stars appear. They act briefly. They seed the universe with the first heavy atoms. Subsequent generations follow different physical rules. Carl Sagan captured this continuity in a single sentence that remains grounded in astrophysics. The cosmos is within us. We are made of star stuff. The statement is not metaphorical. It is a summary of nuclear history. Carbon in organic molecules, oxygen in water, iron in blood, all trace back to stellar interiors. The phrase compresses a long chain of evidence into accessible language without sacrificing accuracy. Modern observatories extend this chain backward. The James Webb Space Telescope measures spectra of early galaxies with unprecedented sensitivity. Its data allow astronomers to test whether observed systems already contain metals or remain close to primordial composition. Early results show that even very young galaxies exhibit some enrichment, implying that the first stars acted quickly. The lack of completely metal-free systems in JWST surveys does not negate population 3 stars. It constrains how briefly they dominated and how efficiently they transformed their surroundings. The logic remains disciplined. If heavy elements exist today, stars must have produced them. If stars produced them, the first stars must have formed without inheritance. If metal-free stars formed, they must have altered the universe rapidly enough that direct remnants are rare. Each step follows from measured facts rather than preference. The narrative is built from cause and effect. Seen in this order, the problem takes on a different shape. The question is not why the universe today contains atoms heavier than hydrogen. It is how rapidly that complexity arose from an almost uniform beginning. Population 3 stars provide a physical pathway for that transition without conflicting with established physics. Their role resolves multiple constraints at once, even though direct evidence of their existence has yet to be isolated. As observations improve, metallicity remains one of the most reliable guides. It records how many generations of stars contributed to a given system. It distinguishes gas that has been processed once from gas that has been reworked repeatedly. It ties models of early galaxy formation to measurable traces rather than assumption. Through metallicity, the first stars leave firm limits on what the early universe could and could not have produced. Those limits, in turn, place strong demands on the earliest stellar populations. To shape the universe so quickly, the first stars must have lived briefly, burned intensely, and released enormous amounts of radiation levels, of light that should have left clear imprints on their surroundings. Part 3. Were the first stars so massive that their light should have been impossible to miss? If a single star in the early universe could release as much energy as 1,000,000 suns combined, then a difficult inconsistency appears immediately. The young universe should have looked overwhelmingly bright, yet telescopes do not show a sky saturated with light. This tension is not rhetorical. It comes directly from applying well-tested physics to conditions that existed before metals, dust, and complex galaxies reshaped how stars form and how light travels. The expectation that the first stars were extremely massive arises from a chain of physical constraints, not from stylistic preference. In gas clouds, composed only of hydrogen and helium, cooling proceeds inefficiently. Hydrogen atoms can emit radiation, but only through limited transitions that operate effectively at specific temperatures. Helium contributes even less. Without carbon, oxygen, or dust grains, there are few channels for gas to lose energy as it collapses. As a result, primordial clouds remain warmer during contraction, and warm gas resists breaking apart into small fragments. When fragmentation is suppressed, collapse occurs on larger scales. Instead of forming many small stars, the gas feeds a small number of growing cores. Simulations performed over the past 2 decades, using initial conditions, constrained by cosmic microwave background measurements, repeatedly show this outcome. When metallicity approaches zero, characteristic stellar masses shift upward by orders of magnitude. This is not an isolated result. Independent groups using different numerical techniques reach similar conclusions. NASA-supported models often highlight a representative case, a primordial star with a mass near 100 times that of the Sun. Such a star would have a surface temperature close to 100,000 Kelvin. At these temperatures, the emitted radiation peaks in the ultraviolet. The star's total luminosity scales steeply with mass, meaning that even a single object could outshine entire stellar populations seen in later cosmic times. At first glance, this creates a contradiction with observation. If such stars existed in large numbers, their radiation should have been unmistakable. The early universe should appear intensely luminous, especially during the period when these stars first ignited. Yet surveys of the cosmic dawn show faint galaxies, not a uniformly bright sky. The resolution of this apparent conflict lies not in revising stellar physics, but in understanding how distance, expansion, and time reshape light. Light does not travel through a static universe. As space expands, wavelengths stretch. Radiation emitted in the ultraviolet billions of years ago arrives today as infrared light. The more distant the source, the greater the stretching. For stars forming at redshifts above 10, even the most energetic ultraviolet photons are shifted far beyond the visible spectrum. What began as an intense blaze becomes a faint infrared signal by the time it reaches modern detectors. This transformation is quantitative. Astronomers calculate redshift directly from the expansion history measured by cosmological observations. The same expansion that explains the cosmic microwave background temperature also dictates how early starlight is diluted. Energy spreads over increasing volumes, and photon wavelengths lengthen. The result is a dramatic reduction in surface brightness. A star that appears overwhelmingly bright at its source can become nearly invisible when viewed across 13 billion years of expansion. Instrument design reflects this reality. The James Webb Space Telescope was built specifically to observe infrared wavelengths where redshifted primordial light should appear. Its NIRCam and NIRSpec instruments operate in ranges inaccessible to earlier telescopes. Even so, detection remains challenging. The combination of extreme distance, short stellar lifetimes, and surrounding gas absorption reduces the probability of observing individual primordial stars directly. Another factor further suppresses visibility. Massive stars do not live long. A star with 100 solar masses exhausts its nuclear fuel in only a few million years. Compared to the age of the universe, this interval is brief. Observing such a star requires that it be shining during the narrow window when its light is both escaping its natal environment and traveling toward us. The overlap between formation visibility and observational reach is small. The environment around these stars also matters. Primordial stars form inside dense gas clouds within dark matter halos. Their intense radiation ionizes nearby hydrogen, creating regions filled with free electrons and protons. These regions absorb and scatter radiation. While no dust is present, the gas itself can trap photons, delaying their escape. The spectrum that eventually emerges is shaped by this interaction, often blending the signal of a single star into a more diffuse glow. As a result, astronomers rarely search for individual population 3 stars directly. Instead, they look for collective effects. Hard ultraviolet radiation leaves distinctive imprints on surrounding gas. Helium ionization requires higher energy photons than hydrogen ionization, so the presence of certain helium emission lines indicates unusually hot sources. JWST has detected such features in a small number of distant systems. Each detection is analyzed carefully because similar signatures can arise from clusters of slightly enriched stars rather than a single metal-free giant. This careful distinction reflects the discipline of observational cosmology. Extraordinary luminosity alone is not sufficient evidence. Astronomers combine spectral data, metallicity estimates, and gravitational lensing analyses to constrain source properties. In some cases, gravitational lensing by foreground galaxy clusters magnifies faint background objects, making them accessible to study. Even with this assistance, the signals remain subtle. The absence of a blazing early universe, therefore, does not contradict the existence of massive first stars. It reflects the combined effects of redshift dilution, absorption, and timing. Each effect is grounded in independently tested physics. When these factors are included, models predict that even extremely luminous primordial stars would appear faint and rare to present-day observers. This understanding reframes expectations. The early universe did not need to resemble a continuous fire to host powerful stars. A small number of short-lived massive objects could profoundly influence their surroundings without dominating the sky's appearance. Their radiation could ionize gas, locally trigger chemical changes, and then vanish, leaving only indirect evidence behind. Carl Sagan captured this mismatch between expectation and reality with characteristic restraint when he wrote, "The universe is not required to be in perfect harmony with human ambition." The statement applies here with precision. Human intuition expects brightness to be obvious. The universe operates according to scale, distance, and time, not perceptual convenience. Modern observations continue to test this framework. JWST surveys push deeper into the infrared probing epochs, closer to the onset of star formation. Each dataset refines limits on how many massive stars could have formed and how bright they could have been without being seen directly. These limits feed back into simulations, narrowing the range of viable initial mass distributions. What emerges is a consistent picture. The first stars were likely massive and extremely hot. Their light was intense at the source, but transformed by cosmic expansion. Their lifetimes were short, and their environments absorbed much of their radiation. The combination explains why the early universe does not appear uniformly bright, even if its first stars were extraordinary. The consequences of the first stars matter more than whether they were ever directly seen. Their deaths, violent or quiet, controlled how the first heavy elements were dispersed and how the earliest black holes took shape. In those final moments, stellar mass and internal structure determined whether material was flung outward into surrounding space or locked away behind newly formed horizons. That uncertainty remains central. If the most massive early stars exploded, their radiation and debris should have left clear signatures. If they collapsed instead, much of their influence may be hidden, preserved only through indirect traces that survive long after the stars themselves vanished. Part 4. Did the first stars live fast and die too soon for us to catch them? What if the universe's first stellar giants truly existed, yet each one disappeared before the earliest galaxies had time to fully assemble, leaving almost no chance for us to see them alive? This possibility is not a dramatic flourish. It follows directly from how massive stars behave when their fuel supply, internal pressure, and radiation output are pushed to extremes far beyond anything seen in the present universe. The lifetime of a star is governed by a simple physical balance. Nuclear fusion in the core releases energy, creating outward pressure that counters gravity. The more massive a star becomes, the stronger gravity pulls inward, and the hotter the core must burn to maintain equilibrium. This increased burning rate does not extend a star's life, it shortens it. A star with a mass similar to the Sun can burn hydrogen steadily for billions of years. A star tens or hundreds of times more massive consumes its fuel at an enormously accelerated pace. Astrophysical calculations, supported by observations of massive stars in nearby galaxies, show that a star with 100 solar masses may live only 2 to 3 million years. In cosmic terms, this is an instant. During that brief interval, the star emits intense ultraviolet radiation, ionizing surrounding gas and altering its environment. Then the fuel in its core is exhausted and gravity regains control. The star's visible life ends almost as soon as it begins. In the early universe, this effect becomes even more pronounced. Population 3 stars are expected to be both massive and hot, lacking metals that would otherwise moderate their structure. Their cores reach higher temperatures. Their radiation output is stronger. The balance between pressure and gravity is maintained only briefly. The result is a population of stars that shine fiercely but fleetingly. This has direct observational consequences. The probability of detecting an object depends not only on its brightness, but also on how long it exists. Even if population 3 stars were extraordinarily luminous, their short lifetimes reduce the chance that they overlap with the period during which telescopes can observe their light. When combined with the vast distances involved, the odds diminish further. In this context, absence does not imply insignificance. A small number of short-lived stars can have an outsized impact on their surroundings. Their ultraviolet radiation ionizes hydrogen in nearby regions, transforming neutral gas into plasma. This process contributes to cosmic reionization, a major transition in the universe's history. Measurements of reionization from cosmic microwave background polarization and quasar absorption spectra indicate that ionizing sources were active early, even if those sources were not numerous. The chemical effects are equally important. Massive stars act as furnaces where heavier elements are assembled. When such stars die, they release these newly formed atoms into space or lock them into compact remnants. Either outcome alters the chemical composition of the surrounding medium. Even a single supernova can enrich a large volume of gas, changing how subsequent stars form. Evidence for this process appears in the oldest stars observed today. In the halo of the Milky Way, astronomers have identified stars with extremely low metal content. These objects formed from gas that had been enriched only once or twice. Their chemical abundance patterns are not random. Ratios of elements such as carbon, magnesium, and iron match predictions for enrichment by massive early stars. In some cases, the patterns are consistent with a single progenitor event. This kind of stellar archaeology relies on careful measurement rather than assumption. High-resolution spectroscopy allows astronomers to determine elemental abundances with precision. Each line in a spectrum corresponds to a specific atomic transition. The strength of those lines encodes the star's chemical history. When models of stellar evolution are applied, they trace those histories back to likely sources. The picture that emerges is one of rapid transformation. The first stars form. They burn intensely. They die quickly. Their surroundings change almost immediately. Subsequent generations of stars inherit an environment that is no longer pristine. Metallicity rises. Cooling becomes more efficient. Star formation shifts towards smaller masses. The window during which truly metal-free stars dominate is narrow. This narrow window helps explain why direct detection remains elusive. By the time galaxies grow large enough to be easily observed, population 3 stars have already vanished. What remains are their fingerprints rather than their light. Ionized gas regions, sudden jumps in metallicity, and unusual abundance patterns serve as indirect evidence of their activity. Modern observatories are designed with this reality in mind. The James Webb Space Telescope does not search only for individual stars. It studies the integrated light of early galaxies and the spectral features of surrounding gas. Emission lines reveal the hardness of radiation fields. Metallicity estimates constrain prior enrichment. Each observation adds a piece to the timeline. This method reflects how science advances when direct observation is limited. Rather than relying on a single detection, astronomers assemble converging lines of evidence. Chemical data from ancient stars, ionization measurements from distant galaxies, and theoretical models constrained by laboratory physics all point toward the same conclusion. The first stars were few, massive, and short-lived. Their influence outlasted their visibility. Historical context reinforces this approach. When nuclear fusion was first proposed as the energy source of stars in the early 20th century, it was not immediately observable. The theory gained acceptance because it explained multiple independent facts, from stellar lifetimes to elemental abundances. Population 3 stars occupy a similar position today. Their existence explains observed enrichment patterns and reionization constraints, even if no single star has been seen directly. Carl Sagan expressed confidence in this cumulative process when he wrote, "Somewhere, something incredible is waiting to be known." The statement captures a methodological stance rather than an emotional one. Knowledge advances by recognizing where evidence converges, even when direct images are absent. The idea that the first stars lived fast and died young therefore resolves several tensions at once. It explains why massive stars could shape the early universe without dominating its visible appearance. It accounts for the rapid onset of chemical complexity. It clarifies why modern telescopes find enriched systems even at early times. Each element of the explanation rests on established physics, applied consistently across scales. As research continues, models are refined and tested against new data. JWST observations extend spectral coverage and sensitivity. Surveys of metal-poor stars improve statistical samples. Supernova simulations explore a wider range of progenitor masses. With each step, the constraints tighten. The window for population 3 activity becomes clearer even if the stars themselves remain unseen. The final moments of the first massive stars are decisive. Their deaths shaped not only the chemical makeup of the early universe, but also the emergence of its first compact objects. Whether a star ended in a violent explosion or collapsed directly into a black hole determined how much material was returned to surrounding space and how the earliest gravitational seeds were established. That distinction matters because it fixes what survived those events. Explosions redistribute mass and energy outward. Direct collapse locks much of that mass away, altering both enrichment and the population of black holes that followed. The balance between these outcomes defines what traces the first stellar lives could leave behind. Part 5. Did they explode? Or collapse straight into black holes without a firework? If the first stars ended their lives by collapsing directly into black holes, then a profound consequence follows immediately much of the evidence for 5. Their existence may have vanished along with them. This possibility is not a narrative flourish. It emerges naturally when the known physics of massive stars is applied to conditions in the early universe, where mass temperature and composition pushed stellar evolution into regimes rarely encountered today. The final stage of a star's life is determined primarily by its mass. This principle has been confirmed through decades of observation and modeling of stellar populations in nearby galaxies. Stars similar in mass to the Sun exhaust their fuel slowly and end as white dwarfs. More massive stars undergo core collapse, often producing supernova explosions that scatter newly formed elements into space. But when stellar mass increases beyond certain thresholds, the outcome becomes less certain and more extreme. For very massive stars, especially those formed from metal-free gas internal structure, differs in important ways. Metals contribute to opacity, which regulates how radiation flows outward from a star's core. Without metals, radiation escapes more freely. This alters pressure, balance, and core evolution. As a result, the path to collapse or explosion depends sensitively on mass and internal conditions. Astrophysical models identify multiple end states for primordial stars. In one scenario, stars within a specific mass range undergo violent explosions known as pair instability supernovae. In these events, extremely high core temperatures allow energy to convert into matter and antimatter pairs. This reduces pressure, abruptly triggering collapse, followed by a runaway explosion that completely disrupts the star. No compact remnant remains. All material is expelled into space, enriching the surrounding medium with heavy elements in a single event. Evidence for such explosions has been sought in the chemical signatures of ancient stars. Certain abundance patterns, particularly large amounts of elements such as oxygen and magnesium relative to iron, align with predictions for pair instability yields. However, these patterns are rare. Their scarcity suggests that while such explosions may have occurred, they were not the dominant fate of all massive population 3 stars. Beyond this mass range lies a different outcome. For stars, even more massive gravity overwhelms all opposing forces at the end of nuclear burning. The core collapses inward and no explosion follows. Instead, the star implodes, forming a black hole directly. In this case, little or no material escapes. Newly formed elements remain trapped behind an event horizon. From an external perspective, the star's life ends quietly. This direct collapse pathway has significant implications. If many of the first stars followed it, then chemical enrichment would proceed unevenly. Some regions would receive metals from explosive deaths, while others would remain nearly pristine. Observationally, this could explain why certain ancient stars show signs of limited enrichment, consistent with only one or two prior events. Observations of distant quasars reveal black holes with masses of billions of solar masses existing less than 1 billion years after the Big Bang. Growing such massive objects from small stellar remnants through ordinary accretion is difficult within the available time. Starting from larger seeds formed by direct collapse eases this constraint. A black hole born with tens or hundreds of solar masses has a significant head start. This connection between stellar death and black hole growth is supported by theoretical work and by observations of early active galaxies. JWST and other observatories detect luminous quasars at high redshift, implying rapid black hole assembly. Models incorporating direct collapse remnants align more naturally with these observations than those relying exclusively on smaller seeds. The absence of clear supernova signatures from the earliest epochs further strengthens this line of reasoning. If explosive deaths were common, astronomers would expect to see widespread and uniform metal enrichment early on. Instead, metallicity measurements show significant variation. Some regions appear enriched quickly, while others lag behind. This patchiness is consistent with a mix of explosive and silent endings. Interpreting these patterns requires careful attention to data. Supernova remnants fade over time, and their detectability depends on environment and distance. Yet the chemical record persists. Spectra of metal-poor stars, absorption lines in distant galaxies, and simulations constrained by laboratory nuclear physics all contribute to a coherent picture. The evidence does not point to a single universal fate for the first stars. It points to diversity. This diversity is not unexpected. Stellar evolution is sensitive to initial conditions. Slight differences in mass or rotation can lead to drastically different outcomes. In the early universe, where conditions varied from halo to halo, a range of endings would naturally emerge. Some stars enriched their surroundings dramatically. Others vanished into black holes carrying their material with them. The scientific challenge lies in quantifying how common each pathway was. Researchers compare predicted yields from different supernova models with observed abundance distributions. They test whether direct collapse rates can account for early black hole populations. They refine simulations to include feedback from radiation and gravity. Each iteration tightens constraints without relying on assumption alone. Historical parallels help clarify this process. When neutron stars were first proposed, they were purely theoretical. Their existence was later confirmed through pulsar observations, which revealed objects matching predicted properties. Black holes followed a similar trajectory. Direct collapse remnants of the first stars occupy a comparable position today. They are inferred from converging evidence rather than direct observation. Richard Feynman captured the spirit of this uncertainty when he said, "I think nature's imagination is so much greater than man's." The statement reflects humility before data. Nature is not obligated to choose the most visible or dramatic outcome. It follows physical laws, even when the results are difficult to detect. Understanding whether the first stars exploded or collapsed quietly reshapes how astronomers interpret the early universe. It influences models of chemical enrichment, black hole growth, and galaxy formation. It also determines where to search for remaining evidence. Explosions leave metals. Collapses leave mass. Both leave traces, but in different forms. As observations improve, especially with infrared spectroscopy and deep field surveys, researchers continue to test these scenarios. JWST extends the reach of chemical measurements to earlier times. Ground-based telescopes complement this work with detailed studies of ancient stars closer to home. Together, these efforts aim to reconstruct events that occurred billions of years ago using evidence available today. The picture that emerges is complex, but consistent. The first stars did not share a single fate. Some ended their lives in powerful explosions that reshaped their environment. Others collapsed directly into black holes, effectively removing themselves from the visible record. Both outcomes fit within established physics and help explain observed patterns. The balance between explosion and collapse determines what evidence can still exist today. If early stars exploded, their influence was spread widely and diluted over time. If they collapsed directly, much of their imprint would remain compact and difficult to detect. In either case, the remnants of those events would not appear as bright sources, but as faint signatures embedded within galaxies, black holes, and the oldest surviving stellar populations. Those signatures are not confined to the distant universe. Some may persist much closer than expected, preserved in environments that have changed little since the earliest epochs. Part 6 is the best evidence hiding in living fossils inside our own galaxy. What if the clearest trace of the first stars is not waiting at the far edge of the observable universe, but moving quietly through our own galaxy, embedded in small, dim stars that formed before the Milky Way fully took shape? This idea shifts the search for the universe's earliest light away from extreme distances and toward a different kind of record, one written not in brightness but in chemistry. In astronomy, time does not erase everything. Some objects persist long enough to preserve conditions from an earlier era. Low-mass stars, unlike massive ones, burn their fuel slowly. A star with less mass than the Sun can survive for tens of billions of years. If such a star formed early enough, it can still exist today, carrying within its atmosphere a chemical imprint of the gas from which it formed. This is the foundation of stellar archaeology. Astronomers call the most chemically primitive of these objects ultra-metal-poor stars. Their defining feature is not age alone, but composition. Their atmospheres contain extremely small amounts of elements, heavier than helium. In some cases, iron abundances are less than 1/10,000th of the Sun's. Such values are not produced by gradual enrichment over many stellar generations. They point to gas that was touched by only one or a few enrichment events. The logic behind this interpretation is direct. Each supernova releases a characteristic mix of elements into its surroundings. The relative amounts of carbon, magnesium, calcium, and iron depend on the mass and explosion mechanism of the progenitor star. When a low-mass star forms from that enriched gas, it locks those ratios into its atmosphere. Because the star's outer layers remain largely unchanged over time, the ratios can be measured billions of years later using high-resolution spectroscopy. This method turns stars into historical records. Astronomers do not observe the first supernovae themselves. They infer them by reading the chemical patterns left behind. A single enrichment event produces a distinctive signature. Multiple events blur that pattern. Ultra-metal-poor stars often show sharp, uneven abundance ratios that are difficult to explain unless only one massive explosion contributed most of the metals. Surveys of the Milky Way halo have revealed dozens of such stars. They are typically found far from the galactic disk, moving on elongated orbits. Their kinematics suggest they formed before the galaxy settled into its present structure. In effect, they are older than the Milky Way as we recognize it today. Their existence confirms that some low-mass stars formed very early, even when the surrounding universe was chemically simple. The discovery of these objects was not accidental. It followed decades of increasingly sensitive surveys and improvements in spectroscopic techniques. Large sky surveys identified candidate metal-poor stars based on broad spectral features. Follow-up observations with high-resolution instruments then measured individual elemental lines. Each confirmed ultra-metal-poor star refined the picture of early chemical evolution. What makes these stars particularly valuable is their selectivity. They do not record the average history of the universe. They record specific events. Some show elevated carbon relative to iron, a pattern consistent with enrichment by faint supernovae from massive progenitors. Others match predictions for pair instability explosions, although such cases are rare. Each star narrows the range of possible properties for the first stellar generations. This approach has transformed the study of population 3 stars. Instead of asking where those stars are, now astronomers ask what they left behind. The answer is found in abundance patterns that cannot be produced by later stellar populations alone. These patterns act as constraints. Any model of early star formation must reproduce them. Models that fail to do so are ruled out. The work requires caution. Stellar atmospheres can be altered by internal mixing or by accretion of material over time. Astronomers account for these effects by comparing observations with detailed stellar evolution models. They focus on elements that are least affected by later processes. This careful filtering strengthens the reliability of the conclusions. The picture that emerges is consistent across independent lines of evidence. Ultrametal-poor stars indicate that early enrichment was sparse and uneven. This supports scenarios in which only a small number of massive stars formed initially, each influencing a large region. It also aligns with reionization models that require intense radiation sources without demanding enormous numbers of stars. This form of investigation resembles forensic science more than direct observation. The stars being studied are not the ones responsible for the original events. They are witnesses preserving chemical traces that point backward in time. The absence of the original actors does not weaken the case. It strengthens the need for careful interpretation. Modern observatories extend this approach. Space-based telescopes provide precise elemental measurements free from atmospheric interference. Ground-based facilities contribute larger samples and long-term monitoring. Together, they build a statistically meaningful archive of ancient chemical records. Each new star added to the sample refines constraints on early stellar populations. This cumulative method reflects a broader principle in science. Evidence does not require belief. It requires consistency. As Neil deGrasse Tyson has said, the good thing about science is that it's true whether or not you believe in it. The chemical signatures in ultrametal-poor stars exist independent of interpretation. The task is to understand what physical processes could have produced them. The implications extend beyond stellar history. These stars inform models of galaxy formation, black hole seeding, and the timing of reionization. They anchor theoretical work to observable facts. In doing so, they bring the study of the first stars closer to home, literally and figuratively. As surveys continue, astronomers expect to find even more primitive examples. Each discovery tightens limits on how metal-free the early universe remained and for how long. The search does not depend on reaching farther into space. It depends on reading the records already present within our galaxy. Chemical fossils in the Milky Way cannot be interpreted in isolation. They must be consistent with what is observed in distant early galaxies, where the first generations of stars were already shaping their surroundings. Considered together, these two lines of evidence connect the earliest stars to the structures observed in the universe today. That connection places a clear requirement on interpretation. If any direct candidates from the first stellar generation exist, present observations must already contain hints of them. At the same time, similar appearances may still arise from later processes, making it necessary to determine whether what is being seen truly belongs to that earliest population or only resembles it. Part 7. Did JWST finally catch a real candidate? Or are we seeing something that only looks like population 3? If a distant cluster shows a spectrum that appears almost untouched by heavy elements, the immediate challenge is not excitement, but proof. In the early universe, youth alone can mimic primitiveness, and separating a truly metal-free population from one that is merely young and faint requires discipline grounded in physics, not headlines. The James Webb Space Telescope was designed to confront exactly this difficulty. Its infrared instruments allow astronomers to examine light that left its source when the universe was only a few 100 million years old. At those epochs, galaxies are small, star formation is intense, and metallicity can be low even without it invoking population 3 stars. This overlap in observational appearance creates a narrow path that data must follow to support any claim of a genuine first-generation candidate. The criteria begin with radiation hardness. Population 3 stars formed from metal-free gas are expected to be extremely hot. Their radiation should contain a large fraction of high-energy photons capable of ionizing not only hydrogen but also helium. In spectroscopy, this expectation translates into specific emission features. One of the most discussed is the helium line, at a rest wavelength of 1,640 angstroms, which appears in the infrared when redshifted from the early universe. Detecting this line with sufficient strength suggests an unusually hot source. Yet this signature alone is not decisive. Young, metal-poor stellar populations can also produce hard radiation, especially if they contain massive stars formed in dense clusters. Distinguishing between these possibilities requires additional constraints. Astronomers examine the absence or weakness of metal emission lines. Oxygen and carbon lines are particularly informative. If such lines are present even at low levels, they indicate prior enrichment. A truly pristine system should show no detectable contribution from these elements within the sensitivity limits of the instrument. This is where JWST's capabilities matter. Its near-infrared spectrograph provides high-resolution spectra that allow precise measurement of faint features. The data must be modeled carefully, accounting for instrument response, background noise, and the effects of intergalactic absorption. Each step reduces ambiguity. The process is slow by design. Gravitational lensing adds another layer. Massive foreground galaxy clusters bend spacetime magnifying light from background objects. This natural amplification can bring otherwise invisible systems into view. Some of the most intriguing candidate regions identified by JWST owe their detectability to lensing. Without it, their signals would fall below detection thresholds. Lensing does not alter the intrinsic spectrum, but it allows astronomers to study sources that would otherwise remain inaccessible. One such candidate, often discussed in the literature, lies in a strongly lensed region, where a compact source shows unusually strong helium emission relative to hydrogen and minimal metal signatures. The object is small, consistent with a cluster of very massive stars rather than a mature galaxy. Its environment appears chemically simple. These properties place it near the boundary where population 3 models operate. However, proximity to a boundary is not proof of crossing it. Astronomers test whether the observed spectrum can be reproduced by metal-poor population 2 stars under extreme conditions. They vary parameters such as stellar mass distribution age and gas density. If a plausible combination exists that fits the data without invoking metal-free stars, the claim weakens. This approach reflects standard scientific practice. Models must be excluded systematically, not assumed away. The tension arises because early galaxies evolve rapidly. A cluster that appears pristine today may be enriched tomorrow on cosmic timescales. Even a single supernova can raise metallicity enough to alter spectral signatures. Observations capture only a moment. Interpreting that moment requires understanding how quickly conditions change. This uncertainty does not diminish the value of candidates. It enhances it. Each potential detection becomes a stress test for stellar evolution models. If data consistently push toward extreme parameters, the case for population 3 involvement strengthens. If not, models must accommodate how ordinary processes can produce extraordinary appearances. Either outcome advances understanding. The role of caution is central here. Carl Sagan summarized this stance succinctly when he said, "Extraordinary claims require extraordinary evidence." In practice, this means requiring multiple independent indicators that converge on the same conclusion. Hard radiation, near-zero metallicity, compact morphology, and contextual consistency with reionization models must align. One feature alone is insufficient. JWST observations are already reshaping expectations. They reveal galaxies that are brighter and more chemically evolved at early times than previously thought. This finding narrows the window during which population 3 stars could dominate. It suggests that enrichment proceeded rapidly, leaving little time for pristine conditions to persist. Candidates that appear near this window therefore carry added significance, but also added scrutiny. Historical context reinforces this approach. When quasars were first identified, their extraordinary luminosities led to speculation and debate. Only through careful spectral analysis and theoretical development did their nature as active galactic nuclei powered by black holes become accepted. Population 3 candidates occupy a similar stage today. Initial signals provoke interest, but acceptance requires sustained evidence. Another complication lies in spatial resolution. At extreme distances, even JWST cannot resolve individual stars. What appears as a single source may be a small cluster. Integrated light blends contributions from multiple objects. Interpreting such spectra requires assumptions about cluster composition. Astronomers address this by exploring ranges of cluster size and stellar mass distributions consistent with the data. The goal is not to force a conclusion, but to map the space of possibilities. The process resembles detective work, but grounded firmly in measurement. There is no reliance on visual drama. Instead, there is careful attention to line ratios, continuum shapes, and environmental context. Each candidate is treated as a hypothesis to be tested, not as confirmation. This restraint preserves credibility and ensures that conclusions remain anchored to evidence. As JWST continues its surveys, the sample of early objects grows. Statistical patterns begin to matter as much as individual cases. If multiple systems exhibit the same extreme characteristics under different conditions, the likelihood of a genuine population 3 contribution increases. Conversely, if each case can be explained by variations of known populations, the search refines its criteria. The outcome so far is balanced. JWST has not delivered unambiguous proof of metal-free stars. It has delivered something equally valuable: constraints. These constraints sharpen models of early star formation, limit the duration of pristine epochs, and clarify how quickly the universe transitioned to chemical complexity. This clarity feeds back into broader questions. Understanding whether any current observations capture true population 3 candidates affects interpretations of reionization, black hole seeding, and early galaxy growth. It determines how much influence the first stars had relative to their successors. The investigation therefore remains open but disciplined. Each new dataset is weighed against established physics. Each candidate is examined from multiple angles. Progress is measured not by declarations, but by narrowing uncertainty. If direct candidates remain ambiguous, the problem moves to a larger scale. The focus shifts to how early cosmic transitions unfolded across the universe as a whole, and whether the timing of those transitions can be constrained tightly enough to determine how many first stars were required. Those constraints depend on understanding how the universe progressed from an opaque state to one that became transparent, and why the schedule of that transition remains difficult to establish. Part 8. If they powered reionization, why is the timing still so hard to pin down? The universe did not become transparent all at once, yet every measurement tells us it did not remain opaque for long, and this tension defines one of the most precise problems in modern cosmology. After the Big Bang, matter cooled into neutral hydrogen and helium filling space with gas that absorbed energetic light. This period, often called the cosmic dark ages, ended when radiation from the first luminous sources ionized that gas, allowing light to travel freely across vast distances. The transition is known as reionization, and its timing remains stubbornly difficult to determine with precision. Population 3 stars enter this discussion not as speculation, but as a physically motivated source of ionizing radiation. Their expected properties follow directly from earlier conditions. Metal-free gas forms stars that are massive and hot. Hot stars emit large numbers of high-energy photons. These photons are capable of stripping electrons from neutral hydrogen atoms. In simple terms, if such stars existed in sufficient numbers, they would have been efficient at reionizing their surroundings. The difficulty lies not in understanding the mechanism, but in reconstructing the sequence. Reionization was not a single event. It was a process that unfolded over hundreds of millions of years unevenly across space. Some regions ionized early, others later. The universe transitioned from mostly neutral to mostly ionized, through a patchwork of expanding bubbles driven by radiation sources whose identities and abundances varied with time. Astronomers infer this process using multiple independent probes. One of the most important comes from the cosmic microwave background. Measurements of polarization by missions such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite reveal how much free electron scattering occurred along the line of sight. This scattering depends on when and how extensively reionization took place. The result is an average constraint, not a detailed timeline. It tells us that reionization was well underway by a certain epoch, but not exactly how it progressed region by region. Another line of evidence comes from distant quasars. When the light from a bright quasar passes through intergalactic gas, neutral hydrogen absorbs specific wavelengths, creating dark gaps in the spectrum. The prevalence of these gaps changes with redshift. Observations show that by around 1 billion years after the Big Bang, most of the hydrogen between galaxies was ionized. Before that, absorption features become more prominent. These measurements provide snapshots rather than a continuous record. Early galaxies, observed with modern telescopes, add a third perspective. Their ultraviolet luminosity functions indicate how much ionizing radiation galaxies could produce. However, translating luminosity into ionization requires assumptions about how many photons escape the galaxies into intergalactic space. Gas and dust within galaxies can absorb radiation before it escapes. The fraction that leaks out depends on geometry feedback and star formation history. Small changes in this escape fraction significantly alter reionization models. This is where population 3 stars become pivotal. Because they form in chemically simple environments, their radiation may escape more easily. Without dust and with shallow gravitational wells, early star-forming regions could have allowed a larger fraction of ionizing photons to reach the intergalactic medium. If population 3 stars were numerous, they could accelerate reionization even if later galaxies were less efficient. Yet models disagree on how many such stars formed and how long they dominated. Some simulations suggest that population 3 stars were rare and short-lived, contributing only briefly before enrichment shut down metal-free star formation. Other models allow for extended periods of population 3 activity in isolated regions. Each scenario produces a different reionization timeline. The disagreement is not a failure of science. It reflects sensitivity to initial conditions. Small differences in star formation efficiency, feedback strength, or halo mass distribution lead to divergent outcomes. Because reionization integrates effects over large volumes and long times, these differences accumulate. The result is a family of plausible histories rather than a single curve. The James Webb Space Telescope provides new constraints by observing galaxies closer to the reionization epoch than ever before. Its measurements of stellar populations, star formation rates, and metallicities inform models of ionizing photon production. Early results indicate that galaxies appeared and enriched themselves rapidly. This rapid evolution narrows the window during which population 3 stars could dominate, but it does not eliminate their role. It suggests that their contribution may have been intense, but brief. Another complication arises from the structure of the cosmic web. Gas is not distributed uniformly. Dense filaments and voids respond differently to radiation. Ionization fronts propagate faster through low-density regions and stall in dense ones. As a result, the universe becomes transparent in some directions earlier than in others. Observational probes sample these variations unevenly, depending on line of sight. This spatial complexity makes timing difficult to pin down. A measurement along one direction may indicate a mostly ionized medium, while another direction at the same redshift shows significant neutral gas. Reionization is therefore best described statistically rather than deterministically. Population 3 stars influence this statistic by determining how early and how strongly ionizing sources appear. The number of first stars matters enormously. Doubling their abundance does not merely double the ionizing output, it can change the topology of reionization, merging ionized regions earlier and altering the visibility of distant objects. In this way, population 3 stars act as a control parameter. Models that include them predict different patterns of transparency compared to models that rely solely on later galaxies. Despite these complexities, constraints are tightening. Combined analyses of cosmic microwave background data, quasar spectra, and galaxy surveys increasingly favor a reionization process that began early and extended over several 100 million years. This scenario allows room for an early contribution from population 3 stars without requiring them to dominate indefinitely. The intellectual approach here reflects a broader scientific method. Carl Sagan expressed it clearly when he said, "Science is a way of thinking much more than it is a body of knowledge." The challenge is not to memorize dates, but to evaluate how different lines of evidence converge or conflict. Reionization research embodies this approach. Each dataset tests assumptions made by the others. Historical parallels help clarify the process. When the age of the universe was first debated, estimates varied widely. Only by combining stellar evolution theory, cosmic expansion measurements, and nuclear physics did a consistent picture emerge. Reionization follows a similar path. Precision improves as independent methods are reconciled. Population 3 stars remain part of this reconciliation. Their existence explains how ionization could begin early, before large galaxies became common. Their disappearance explains why direct signatures are rare. Their uncertain abundance explains why timing remains difficult to fix precisely. Each element fits within a framework constrained by observation rather than conjecture. As new data accumulate, particularly from deep JWST surveys and forthcoming radio observations of neutral hydrogen, the timeline is expected to sharpen. Models will be refined or set aside according to how well they reproduce the observed patterns. The remaining uncertainty is not a casual gap in knowledge, but a reflection of how sensitive the early universe was to small physical differences. If reionization depended strongly on the number and nature of the first stars, then characterizing that population becomes essential for interpreting the large-scale structure observed today. Under that dependence, it becomes necessary to consider whether some of the most luminous early objects might arise from a different physical mechanism altogether, one capable of mimicking the influence of the first stars while operating under different rules. Part 9. Could the first monsters be mistaken for something even stranger like dark stars? If a newborn object in the early universe radiates enormous energy without showing the chemical signatures expected from nuclear fusion, then the breaded's twofer. The problem becomes immediate and serious. The power source itself must be questioned. In recent years, this problem has moved from abstract speculation into active debate, driven by observations of unusually luminous objects at extreme distances that challenge standard interpretations based solely on primordial stars. The idea of a dark star did not arise from a desire to be exotic. It emerged from applying known physics to an unusual environment. In the early universe, dark matter was more densely concentrated within the first gravitational wells. If dark matter particles can annihilate when they encounter one another, then energy would be released. In regions where gas collapses to form stars, dark matter density could rise high enough for this annihilation energy to become astrophysically significant. In this scenario, a forming star does not rely entirely on nuclear fusion to balance gravity. Instead, energy from dark matter annihilation heats the gas from within, slowing contraction. The object grows larger in radius, but remains relatively cool at its surface compared to a fusion-powered star of similar mass. The result is a luminous object with properties that differ subtly, but importantly from those of population 3 stars. This distinction matters because population 3 stars are expected to be extremely hot. Their metal-free composition leads to compact structures and high surface temperatures, producing hard ultraviolet radiation. Dark stars, by contrast, would emit light with a softer spectrum even while maintaining high luminosity. The difference is not merely academic. It translates directly into observable signatures. Spectroscopy provides the primary tool for separating these possibilities. Fusion-powered primordial stars produce intense radiation, capable of ionizing helium efficiently. This leads to strong helium emission features under the right conditions. Dark stars with lower surface temperatures would produce fewer such photons. Their spectra would lack the same helium ionization strength, even if total luminosity were comparable. Metallicity provides another decisive test. A genuine population 3 star forms from pristine gas and begins enriching its environment almost immediately through radiation and eventually stellar death. Dark stars, if sustained primarily by dark matter annihilation, could delay nuclear fusion and therefore delay metal production. Detecting oxygen, carbon, or other heavy elements in the surrounding gas places strong constraints on how long a dark star phase could persist or whether it occurred at all. This is why oxygen detection plays such a central role in current debates. Even a small amount of oxygen indicates prior stellar processing. JWST has already demonstrated sensitivity to faint metal lines in early galaxies. When such lines are present, they challenge models that require prolonged metal-free conditions. When they are absent within tight limits, the door remains open for alternative power sources. Some JWST observations have revealed compact luminous objects with properties that sit uncomfortably between standard categories. Their brightness suggests high mass. Their spectra sometimes lack strong metal lines. Their helium features are ambiguous. Each case forces astronomers to consider whether extreme population 3 clusters alone can explain the data, or whether a different engine must be included. Importantly, dark stars are not proposed as replacements for population 3 stars. They are proposed as competitors in specific regimes. Even if they exist, they would form under limited conditions and for limited durations. Their relevance depends on dark matter properties that are still unknown, including particle mass and annihilation cross-section. This dependence makes dark star models testable rather than unfalsifiable. The scientific process here is explicit. Researchers build models that predict luminosity size and spectral output for dark stars under different assumptions. These predictions are compared with observed candidates. If no parameter set reproduces the data better than standard stellar models, the dark star hypothesis weakens. If, however, dark stars provide a more natural explanation without violating other constraints, the hypothesis gains weight. This comparative approach reflects a disciplined view of uncertainty. As Richard Feynman stated, it is scientific only to say what is more likely and what is less likely. The goal is not to declare winners prematurely, but to rank explanations based on how well they fit the full body of evidence. Historical perspective reinforces this caution. Many astrophysical objects were once misclassified because their power sources were unknown. Quasars were initially mysterious radio sources with no obvious explanation. Only after spectral analysis and theoretical development did their nature as accreting black holes become clear. Dark stars, if they exist, would represent a similar phase where interpretation lags behind observation. At the same time, the dark star idea faces serious challenges. Dark matter annihilation rates must be high enough to power a star without exhausting the local dark matter supply too quickly. The stability of such objects over time is uncertain. Feedback from radiation could disperse the surrounding dark matter halo, shutting off the very mechanism that sustains the star. These issues are active areas of research rather than settled conclusions. JWST's role in this debate is central. By extending spectroscopic sensitivity and spatial resolution, it allows astronomers to test predictions that were previously inaccessible. Measurements of line ratios, continuum slopes, and environmental metallicity constrain the range of viable models. Each observation narrows the parameter space where dark stars could operate. The broader implication is methodological. The early universe may host objects that do not fit neatly into familiar categories. Determining whether such objects represent extensions of known physics or evidence of new processes requires patience and rigor. Dark stars exemplify this challenge. They force astronomers to consider how incomplete knowledge of dark matter intersects with observable phenomena. As data accumulate, the balance of likelihood will shift. Some candidates may resolve into clusters of massive primordial stars. Others may reveal signatures inconsistent with fusion alone. The outcome will depend on measurement, not preference. What remains clear is that the presence or absence of dark stars has implications beyond classification. It affects estimates of ionizing photon budgets, early chemical enrichment, and the growth of massive objects in the young universe. Even a brief dark star phase could alter timelines derived from simpler models. The investigation, therefore, continues with restraint. Each proposed candidate is examined as a physical test, not as confirmation. Competing explanations are weighed side by side. The universe is allowed to choose which path it followed. Comparisons across observations place increasing weight on indirect evidence. If population 3 stars were rare, short-lived, and at times indistinguishable from other luminous phenomena, then the central issue becomes whether their existence can be established beyond reasonable doubt without ever observing them directly. That determination depends on whether all available constraints taken together consistently point to a dominant early stellar population that shaped the young universe, even if none of its members remain visible today. Part 10. If we never see a single population 3 star directly, can we still prove they once ruled the sky? What if the first stars are gone forever, erased as individual objects, yet the universe around us still carries an unbroken record of their existence, written not in light, but in structure, composition, and constraint? This question sits at the end of a long investigation, and it is sharper than it first appears, because science does not require witnesses that remain visible. It requires consistency between cause and consequence. The case for population 3 stars begins with conditions that are no longer debated. Measurements of the cosmic microwave background, combined with laboratory-tested nuclear reaction rates, show that the early universe emerged from the Big Bang with a very limited inventory of elements. Hydrogen dominated, helium followed, lithium appeared only in trace amounts. No carbon, no oxygen, no iron. This chemical simplicity is not inferred indirectly. It is measured. Any explanation of cosmic history must start from this boundary. From that boundary, stellar physics imposes a requirement. Heavy elements do not form spontaneously in interstellar space. They require sustained high temperatures and pressures maintained over long periods. Those conditions occur only in stellar interiors. There is no alternative process in known physics capable of producing the observed abundance of heavy elements across the universe. This establishes a necessary step. If the first stars formed from metal-free gas, then their structure, mass scale, and radiation output are not adjustable parameters. They follow from how gas cools and collapses in the absence of metals. Decades of simulations constrained by gravitational dynamics and atomic physics tested in laboratories converge on the same conclusion. The first stars were massive, hot, and short-lived. This is not an aesthetic choice. It is a consequence of limited cooling pathways. Short lifetimes explain absence. Massive stars exhaust their fuel quickly. In the early universe, this means they disappear before galaxies grow large and stable enough to be easily observed. Their disappearance does not weaken the case for their existence. It sharpens it. A population that must exist, but cannot persist naturally, leaves indirect evidence rather than direct images. That indirect evidence appears in several independent forms. One of the most compelling is chemical. Ultra-metal-poor stars in the Milky Way halo preserve abundance patterns that cannot be produced by many generations of enrichment. Their ratios of carbon, magnesium, calcium, and iron point back to enrichment by one or a few massive progenitors. These stars act as long-lived recorders. Their chemistry is not speculative. It is measured line by line through spectroscopy. Another line of evidence comes from reionization. Observations show that the universe transitioned from neutral to ionized within a relatively short cosmic interval. Achieving this requires intense sources of ionizing radiation early on. Population 3 stars, by virtue of their high temperatures, naturally produce such radiation. Models that exclude them struggle to start reionization early enough without invoking extreme assumptions about later galaxies. Models that include them do not require such adjustments. Black holes add a further constraint. Quasars observed at high redshift host black holes with masses that challenge growth models starting from small remnants alone. Direct collapse from massive early stars provides a plausible pathway to larger initial seeds. This does not prove that all first stars collapsed into black holes, but it shows that at least some likely did. The presence of early massive black holes therefore supports the existence of a massive stellar population before them. Modern observations extend these arguments rather than replace them. The James Webb Space Telescope has revealed galaxies forming earlier and evolving faster than expected. Their chemical enrichment appears rapid, implying that the first stars acted quickly and then vanished. JWST has also identified candidate regions with extremely low metallicity and hard radiation fields. None has yet provided unambiguous proof of a single metal-free star, but each has tightened limits on how such stars could have existed. This tightening is crucial. In science, absence can be as informative as presence when instruments are sensitive enough. JWST's non-detections constrain the duration, abundance, and environments of population 3 stars. Any viable model must now fit within these observational boundaries. The first stars become less like objects and more like conditions that data must satisfy. This shift marks a transition in how the problem is framed. The goal is no longer to find a pristine star shining alone against the cosmic background. The goal is to test whether the universe we observe could exist without such stars ever having formed. When all constraints are applied together, the answer remains no. Without an early population of massive metal-free stars, the observed chemical composition, reionization history, and black hole population cannot be reproduced simultaneously. In this sense, population 3 stars are present even in their absence. They appear as requirements embedded in the data. They define what must have happened, even if the actors themselves are no longer visible. This is not unusual in science. Neutrinos were inferred before they were detected. Black holes were predicted long before imaging. In each case, consistency across independent observations established reality before direct confirmation. Carl Sagan captured this relationship between observation and understanding in a sentence often quoted for its clarity rather than its sentiment. "We are a way for the universe to know itself." In this context, the statement reflects method. By measuring atoms, radiation, and structure, the universe leaves a record of its own past. Our role is to read that record carefully. What remains unresolved is not whether the first stars existed, but how many formed, how long they dominated, and how varied their endings were. These details continue to be refined. Future observations, including deeper infrared surveys and radio measurements of neutral hydrogen, will sharpen timelines further. The framework, however, is already constrained tightly enough to rule out scenarios in which the first stars never played a major role. The arc of evidence now closes with coherence rather than spectacle. Metal-free initial conditions require massive stars. Massive stars explain early enrichment. Early enrichment explains observed chemistry. Intense radiation explains reionization. Black hole seeds explain early quasars. Each link reinforces the others. Remove one, and the structure fails. This coherence is the strongest form of proof available when direct observation is no longer possible. It does not rely on belief or narrative appeal. It relies on compatibility with data across scales and epochs. Population 3 stars satisfy that requirement more completely than any alternative proposed so far. The first stars occupy a clear place in the history of the universe. They are not absent because evidence is lacking. They remain unseen because their role was brief and decisive. Their influence endures in every heavy atom, in the oldest surviving stars, and in the transparent regions of space that now separate galaxies. Thank you for spending this long stretch of time here, following the universe from its simplest beginnings to the structured cosmos observed today. Wishing you a calm, restful night and a peaceful sleep. Good night.